Hello everyone, my name is Pedram and I'm a professor in data analytics. Welcome to another episode of Deep Learning. Okay, Module 5, Deep Computer Vision. This is the second Python video for this module. So let's go to the GitHub repository and get it started. So here is the GitHub repository for the course. You go to the lectures and Module 5, you can get access to the PDF here and of course the notebooks. Last time we talked about how you can build your first basic CNN, and we applied to the MNIST dataset, and we saw that it did a perfect job in classifying the handwritten digits. In this one, we're going to work with Fashion MNIST dataset, and I'm going to apply data augmentation. And actually, I'm going to showcase it to you that what will happen if you just use fully connected layers, deep neural networks, and apply it to an image. And then we are going to compare the performance of that model with a CNN. Okay, so you can go ahead and click on this one. I have already this one open and connected to the GitHub Colab. So if you click on this open in Colab, you should be navigated to the right page. So I already have it open here and it's connected already. Okay, so the GPU is running and everything is ready for us to take off. Okay, so let's go ahead and we're going to run and see what is the TensorFlow version. As of February 2023, this is 2.11. I'm going to import pandas numpy matplotlib for some data manipulation and visualization. And as I said, we are going to work with the Fashion MNIST dataset. So here is the link to the Kaggle page, and here's the dataset. But actually, let me show you what does it contain. So this dataset has 60,000 train images and 10,000 test images, and the image size is 28 by 28. And this, I believe, is 28 by 28. Yeah, it is 28 by 28, and it's a grayscale image, right? So, and what do we have inside this dataset? There are 10 different classes. It goes from 0 to 9. It's already the integer. The target variable is already integer. And 0 is t-shirt, 1 trouser, pullover, dress coat, sandal, shirt, sneaker, bag, and ankle boot. So that's, and the dataset is balanced. So it means that each of these classes have equal numbers of observations. All right, so let's go ahead and import the dataset. So from TensorFlow keras.dataset, let's import Fashion MNIST. And we are going to stick to this tradition that we're going to call it X train, X test, Y train, Y test. You can call it image train or label train. Then let's quickly take a look into the shape. So as I said in the previous video, the shapes are one of the biggest things you should have a good grasp on them, especially if you want to feed it to a neural network for image processing. So, and you should know the ways how to manipulate the shape of an image. Okay, so there are 60,000 28 by 28. So we know that if I want to pass it to a CNN, I have to add this channel, which is 1 for a grayscale. Okay, so this is our test set. We can look at the Y train, again, 60,000. And we can also go ahead and look at I just wanted to show you that the dataset is balanced, right? From collections, I'm going to import counter, and basically it's going to give me the counts in the Y train for different classes, right? So as you can see, there are 10 classes and each of them has 6,000 observations, so it's add up to 60 for the train set. Let's go ahead and take a look at one of them, for example. So the first, this is the second observation in the train set, which is well, we don't know what is it. Let's see, what is the first one? The first one, yeah, it must be a boot, I guess. And now we can see what was the actual train. So the actual class is 9, and we know that 9 was our ankle boot, right? So it is correct. So, and then let's look at the first one, just in case. Yeah, the first one, I don't know, maybe it's a t-shirt. Let's see, what is the label? The label is 0, so 0. Yeah, t-shirt. Okay, so that's it. Now, in the previous video, I also talked about it. This target variable has 10 different classes, and so you can treat it in 2 different ways. This is a multi-class classification, right? And let me actually, so again, these are the ways that you can do that. For multi-class classification, you can do one hot encoding, turn them into dummy variables, 0, 1s. and then use, this is your loss function, categorical cross entropy, or just use integer labels plus a sparse categorical cross entropy, right? And it doesn't make a big difference for some datasets like this one, but you should be aware that if you have a multi-class classification problem like this, it is recommended to use one-hot encoding, especially if the classes are not, they don't have natural ordering, right? So in the previous one, we used MNIST dataset, and MNIST dataset numbers were between 0 and 9. So there is this natural ordering. We went ahead and used the integer labels and added the sparse categorical cross entropy. For this one, because I just wanted to show you how to do it this way, so let's use one-hot encoding. And for the loss function, we're going to use categorical cross entropy. Okay. And here are just some reasons that why the one-hot encoding is preferred to integer labels when there is no natural ordering. So these are the reasons. For example, there's no implied ordering, right? So this, if you do one-hot encoding, it helps you to generalize better. So it does have a better generalization, and of course, it is easier to interpret, right? So now let's look at the shape of the train, the Y train one more time, 60,000. I can do one-hot encoding in two different ways, and at the end of the day, it really doesn't matter which one you pick. So I'm gonna transform the Y train in one way and Y test in another way. So you have seen both ways. So the first one is you can go from tensorflow.keras.utils, import two categoricals, and then I'm gonna use that function. So I'm gonna create a new, I don't override the Y train because I'm going to use it later in the notebook. So I'm going to create a new one, Y train underscore one-hot encoded. And I'm going to use two categorical. So two categorical, pass the Y train and number of classes 10. So here's the shape of the Y train one-hot encoded. Now it goes from 60,000 by 1 to 60,000 by 10, right? Okay, now alternatively, we can use from TensorFlow, we can import you can use the function one-hot. So if I use the function one-hot for the test set, I call it one_test one-hot encoded, and then the depth, this is simply the number of classes. We use the term depth here, is equal to 10. If I look at the shape, now it's a tensor, right? So again, the shape is 10,010 because we have 10,000 observations in the test set. But these are pretty much the same. And if you want to look at the columns, for example, so if I say Y test one-hot encoded, so these are all encoded observations, right? Okay, and now let's go ahead and create an ANN model. Remember, this is a CNN notebook, but I just want to use artificial neural networks, the fully connected layers, just as a benchmark, right? And to remind you how we can do that. So let's see, we're going to import TensorFlow and Keras and layers from Keras. And we can quickly just double check the shape. Again, it's a good idea to constantly keep track of the shape of the data set because you don't get the errors down the road. Okay. So right now it is 60,000 by 28 by 28. I know that I want to use a fully connected layer. So I need to flatten this thing, right? So I need to go ahead and make sure that this 28 by 28 is flattened. And then now I have a 60,000 by that flattened things, right? So each image is flattened by 28 multiplied 28. So this is what I'm going to do. I'm going to go ahead and create an xtrain underscore ANN. So this is for artificial neural network, basically fully connected layers. And I'm going to say, go ahead and reshape the xtrain 60,000, 28 by 28. Remember, we are flattening this thing, this image, right? It's not a matrix anymore. It's going to be a vectorized, it's going to be a vector. And so 28 by 28 is 784. Now we have 784, 60,000 by 784. I'm going to normalize the observations. I'm going to divide them by 255 because we know that each pixel goes from 0 to 255. We do the same thing for test set. If you want to quickly check the new train set shape, now it is 60,000 by 784. So it's ready to be fed to our artificial neural network. So I'm going to go ahead and quickly use sequential approach because we are not going to customize it or play around with it. We are going to just use it as a benchmark. So I'm going to use sequential approach for the ANN model and our own functional API for the CNN model. So let's go ahead and build that. So let's call this model ANN MNIST, and I'm going to add an input layer, the shape of 784, and a dense layer on top of that with 512 units, activation value, and you can call it anything. I call it my first layer. You can just don't specify anything, but in the summary table, numbers are going to get updated. Then finally, we're going to add the output. The output is a dense layer with 10 units, activation softmax, and that's it. So here you go. We can look at the model summary. Because the model was built, if you do this kind of sequential approach, when you're adding layers on top of each other, the build is done automatically. So here are the number of parameters in the model. So remember, we flattened that into 784 values in a vector. So we have to basically multiply that one to the number of nodes in the first layer plus the 512 bias for each node. So this is what we're doing. If I run this, I get 401,920 parameters in the first layer. And in the second layer, again, it's coming from 520 nodes. We have to multiply it by the output layer. So it's 5120 plus 10 bias term, 5130. Okay. Now let's compile the model, make sure that you are using the correct loss function. Remember, we are using one-hot encoding, so your loss function should be categorical cross entropy. Okay, and the metric you're going to use accuracy. Okay, so let's run this, and I'm going to make a model checkpoint. We have seen all these things before, right? So if you feel that I'm rushing through these things, so please make sure you check out the previous video. That's a prereq for this one. And I'm trying to keep this video as short as possible. Okay, so now there's a couple of checkpoints. There's a model checkpoint here, and it's time to fit the model. I'm going to pass a train set, and the validation set I use a test set, and 20 epochs, each batch size of 128, and this callback that we just created. So let's go ahead and run this. And this is gonna, of course, the first epoch is usually taking longer than the other one because it's loading up into the memory, and the rest of them are faster. Okay, so it seems that right off the batch, it's not doing a bad job, right? It's almost 80%, and it's increasing in the validation set, and we'll see how far it can go. And yeah, remember, this is our benchmark. So we're using fully connected layers. You're flattening the image, which is not a good idea for CNN models, right? We talked about it in a lecture video. But for this data set, because it's super simple, the images are almost centered and it's very low resolutional. It seems that, at least by far, we can see that it's doing an okay job, but our goal is to improve this thing, right? Our goal is to improve the performance in the test set, which is, let's see what it is. It is 88%, right? So remember, we save this model as ANN benchmark Keras. So if you go to your folders, you should see it there now, right? So what are we doing? We are saying that go ahead and find the best model. Remember, we use a callback, and the callback save the best model here. Use the best model, make prediction in the test set, report that number. It is 80%, 89%. Now let's see if we can improve that using a CNN. Obviously, the answer better be yes, right? So let's construct our CNN now. Remember, in the CNN, we don't work with flattened data, so we go back to our xtrain, not xtrain underscore ANN. So this is the shape of xtrain, 60,000 by 2828, all good. But I need to reshape it to 60,000, 2828, 1, because this is what the CNN, the conv2D layer, is expecting. So this is the dimension that the conv2D layer is expecting. So again, normalizing things. And I can go ahead and look at the x-shape, the reshaped version, and the x-test reshaped version. So all good. So we are ready to create our CNN now. So I'm going to go ahead. We don't need to import these things again, but I just want to remind you that if you want to look at it as a standalone cell, so you have to make sure you import all these things. Now I'm going to use a functional API approach because we want to play around with this later on, right? So we're defining our CNN builder, again, input layer, and nothing new here, 2828.1. Then we have conv2D max pooling, convolutional max pooling, convolutional, and flattening. I can add a dropout layer after flattening, so you can do it if you wish, but I'm gonna save that for the data augmentation part. And again, we have talked about all the details here, so make sure you check out the previous video, nothing new. And finally, we have our output layer, 10 nodes for 10 different classes, softmax. That's it. Let's go ahead and build a model, keras model. Inputs are inputs, outputs are equal to outputs because this is the way that we name them. You can name them anything. I call it my first CNN. Well, this is not our first CNN anymore, right? So we can call it CNN base model, right? Because in the next iteration, we are going to do CNN augmented model. Make sure you're using the correct loss function. So let's go ahead and create this model. And now we can look at the parameters. And in the previous video, we talked about how we can calculate these parameters, how we can calculate the input and output shape, and etc. Here, just for the sake of time, I'm going to show you only one of them, right? So for example, if I go from input layer to convolutional layer, so what do we have? We're using a 3x3 filter, remember? And that 3x3 filter is applied to one channel. So far I have 1 multiply 3 multiply 3. And then in this convolutional layer, we're applying 32 of those filters. So it needs to be multiplied by 32. And of course, I need to add 32 bias term. So this is what we get. 1 multiplied 3 by 3 by 32 plus 32, right? And you can try out to back out this number, but here are the calculations just to make sure that you can follow. I think it is a good exercise to do it at least, I don't know, a couple of times. Or at least until you feel confident, and then you don't need to look at these numbers anymore, right? And it's not the end of the day if you don't quite get it how these parameters are calculated, but I think it is something that helps you to understand the input shape, output shape, and the number of parameters and things like that better. So generally, I encourage you to learn it. Okay, so the same story for the size of the input output. So for example, how we go from 28 to 26, we say that there's 28, no padding, but the size was 3, so 28 minus 3, divided by stride, which is 1, plus number 1, which you get 26, okay? Again, if you feel that this is a little fast, make sure you check the lecture videos and you check the Python part 1. All right, so we can go ahead and fit the model using a checkpoint. I call this CNN basic, and then the same setup, right? The same setup. Let's look at the trained model. This is also going to be fast because again, this is a simple data set. It's not necessarily super large, and the resolution is small. 28 by 28. And it seems that our CNN model, and by the way, guys, this is a pretty simple CNN model, maybe 3 convolutional layers, couple of pooling layers, and that's it, right? And a dense layer at the end. Well, actually, we didn't use a dense layer at the end. We just flattened things, right? And you can go ahead and add a dense layer here. You can add a dropout layer here, but we just want to use the very basic CNN structure and see how it does out of the batch. Okay, so epoch 14, we are going above 90%, so already this is outperforming the ANN, which should be the case, right? Okay, so let's wait a couple more seconds here, and there you go. So the model is trained. We are going to look at the performance of the model in the test set. Remember, now we have a basic model here. I'm going to load it up, the best version in this 20 epochs, and see what is the performance. It is 91%. Okay, so it's already 3% improvements over the ANN. All right, we can go ahead and look at we have seen these things before, right? I'm going to say make a nice data frame from this history. And then look what is inside that data frame. We have loss in the train and validation set. We have accuracy in the train and validation. All right, so we can go ahead and plot these things. Okay, and so yeah, overall not bad. Our model is learning, and at some point further, let's say from epoch 10, it seems that it's overfitting and it's going back. Okay, all right. Now let's see how we can mitigate this overfitting thing that we're seeing here. So one way is to using data augmentation. Okay, so I want to tell you something right away, that data augmentation does not work all the time necessarily. That depends on so many factors, because the parameters that you use in your data augmentation can be tricky. Data augmentation can add noise, can add additional noise to your image, which is sometimes it's not necessarily good for all the image types. So just be aware. When you're doing data augmentation, do not always expect to get a better performance, right? And that's exactly what we are going to experience here. Okay. There are different ways to do data augmentation in TensorFlow. Historically, I personally used to do it this way. There was this image data generator class, but that has been deprecated. So I'm going to show you how you can work with the newer version. TensorFlow itself recommend using tf.data frame. Use that kind of pipeline instead of this one. So this is still working, but I think you should learn the way that they recommend, right? So remember, this has been deprecated, and they recommend to use tf.data.dataset. And this is the way that we are going to do our notebooks in computer vision. Okay, so let's go back. And this is going to take you long. So for that reason, I already have this run in the other notebook, and I'm going to show you the answers, show you the results for the training part. But the idea is that, what are we doing? We are adding this layer to our neural network, right? So this layer that I'm going to define, I can call it anything. I call it data_augmentation, and it's a sequential layer, right? So I say from Keras sequential, add bunch of these data augmentations, let's say classes, right? So you can do layers.random flip, you can do layers.random rotation, random zoom, and these are very self-explanatory. So you can flip the image horizontally, you can do rotation 10% to the left or right, and you can do zoom 20%, right? So then if you're curious to see what are available augmentation classes, you go ahead and click on this link. So these are the available ones in Keras, right? You can do crop, you can do flip, you can do random translation, you can do rotation, zoom, height. I encourage you to go ahead and try a couple of these things and see which one is working better for your case, okay? Now I have this layer created called data augmentation. Now I can go ahead and pass any input image to this one, and it's going to transform it based on these layers that we just defined, right? So let me actually show you one of the images from the train set. So this is the first image from train set. Let's go ahead and plot that. And in the previous video, we said that if it is a 28 by 28 by 1, we don't need to reshape that one. Either way, it's going to work. And remember, this is a grayscale image. So the reason that you're seeing it's kind of colorful, because the default CMap is something that's showing it this way. If I go ahead and change the CMap to gray, this is actually how the data set is going to look like. Okay, I probably used the wrong one, but you get the idea. I think in the previous one I showed you something. Gray was there. Yes, CMap gray must be there. I don't know. Okay, there must be some typing error here. Okay, you go ahead and figure it out, right? And then we have, so remember, this is I'm gonna go ahead and save this, let's say boot in an object called image. Remember, our image is a 28 by 28 by 1. And I want to apply this data augmentation to the image that I just created, right? And if I don't do this one, I just show you the shape. As you can see, this is going to be a tensor, right? And if I want to plot these things, I have to transform it to NumPy first and then plot it, right? So that's why I added this .numpy here. .numpy, I need parentheses. Okay. Now I can pass this to PLT image show, and I can, for example, visualize 9 of these rotations, right? So what are we doing? We're saying that go ahead and transform these images, this image that I have, this is only one image, in 9 different ways, because I'm going through 0 to 8 or 1 to 9, right? And we're using subplot to just show them 3 by 3, right? So 3 by 3, and then we are going through the, like this 1, 2, 3, 4, 5, 6, okay? So image show, augment image, augmented images, and then NumPy reshape 28 by 28. Again, you don't need to pass this reshape here, but I think it's a good exercise to just keep in mind that what should be the input of this image show. Okay, so you can go ahead and do that. And every single time that I run this line, it's going to go ahead and do a random combination of all these transformations. Okay, all these 3 transformations. Okay, so to the same, to one image. So if I run it like this. As you can see, each time there is flipping going on, rotation going on, and zoom in and out going on, right? All right, so this is how this layer that we just created, data augmentation, works. So here I pass it one image. In the network, we're going to pass all the 60,000 images to that. So that's why it's a little taking more time, right? So remember, here's just a couple of lines that I want you to be aware, because sometimes the network is going to complain. It says that the input shape of the let's say convolutional layer is not compatible with the output of the data augmentation. If you got an error like this, there are ways to handle it, right? So for example, here I'm going to create an X object. I say that go ahead and data augments all the train set. What is the shape? The shape is 60,000 by 28 by 28, right? And then usually the conv layer 1 is expecting a 60,000 by 28 by 28 by 1, right? So how can I add that 1 to the end of it? So you can go ahead from TensorFlow, use expand dimension and add it to the very last dimension. This is how we get it. If you want to reduce it back to the original dimension, you're going to go ahead and TF squeeze the same thing and back it one dimension, right? So here's the part, you know, if the image is grayscale, usually I don't get if color, you have 28 by 28 by 3, usually at this stage I don't get any error. But if you do grayscale, for some reason sometimes it gives you error, sometimes it doesn't. This is a compatibility error, okay? Let me see if I get that error here, and I'll show you how to troubleshoot that. So let's go ahead and run this. Yeah, we get this error, right? And this error basically says that your conv layer number 1 is incompatible with the layer, right? With the previous one. It is expecting a minimum dimension of 4, but it was passed something like this, non-28, 28. So it's expecting non-28, 28, and 1, and we have to fix that, right? So one way to do that, and this incompatibility is just coming from, if you read the first line of the error, the warning, this is warning, not an error, but probably that's part of the reason, right? So here it says that, let me actually go to the very end. It says that one of these rotations was called on an input with incompatible shape, right? So the same story there. So there are a couple of ways to fix this. One is that you can go ahead and play around with these augmentations. And if you come up with a better way, or if you know a better way, just let me know. And then I can go ahead and rerun this thing. I commented out a couple of them. You see that works. So for example, that flipping was working, maybe one of them was not working. So you play around with these things, and then hopefully you can get it to working like this. Or you can go ahead and increase the extension right after the data augmentation layer. So right after here, you can increase the extension. And then right after conv layer, you should decrease the dimension, right? So again, expand dimension after augmentation and squeeze dimension after the first conv layer. So if you practice, if you work with this kind of models for a while, you realize that how you can manipulate the input-output shape of the layers in the network. Okay, so I'm not going to run this one, the model fit, because it's going to take very long, but I have it already run in the previously. So this is, as you can see, each iteration, each epoch is taking 500 seconds. So let's actually show what was the performance. So we get actually, by the way, I added a dropout layer here to make sure that it's not overfitting. Yeah, the old dropout. So it seems that the performance was something around 86-ish%. We know that without data augmentation, we got 91. So here, again, the data augmentation was not that helpful because of multiple reasons. First of all, the original train set is not that small. So usually data augmentation helps with the small data sets, right? So here we have 60,000 observation already. And the images are very low resolution, only 28 by 28, and they were already centered, right? So, and also we added a dropout layer to avoid overfitting. So this means that we could have let this thing run more, right? So maybe 20 epoch was not enough. So we can, again, just for the sake of time, I just ran it 20 epochs, but you can let it run more and hopefully you get a better numbers. So then we can go ahead and plot, again, this is the accuracy in the loss and train for the augmented model, the same story for loss, for the train and the validation for the augmented model. Okay. All right. So now I'm gonna go ahead and go back to our CNN basic model for the rest of the notebook. So the first one, so I'm gonna say go ahead and pick the best CNN basic model when we save it here, and quickly check out the summary again. So these are the numbers that we talked about, 104,000 parameters. And finally, we can go ahead and make some predictions in the test set, right? So I'm going to create this object called prediction probabilities. As we talked about it in the last video, the model is going to predict some probabilities for each observation in the test set because we use the softmax function. We have 10 classes. So for example, this is the prediction probabilities or probability predictions for the first observation in the test set. And let's see what is the argmax of that. So it says that the first observation should be in a test that should be a 9. Let me see if I have the classes here down here. Yeah, 9 was an ankle boot, and they actually in the test, the label in the test set, the actual label was also 9. So the model was able to capture this first observation in the test set correctly. And so, but we said that in order to just see the confusion matrix, classification reports, and things like that, we need to transform these probabilities into classes, right? So for each observation, we're going to look into the argmax, and that's going to be the class. So here, this is what I'm creating predictions using NumPy argmax and passing the probabilities and doing that argmax on the column base. So let's look at the first 5 observations in the test set, 9, 2, 1, 1, 6. So these are the classes. And now I'm going to go ahead and import classification report and confusion matrix from the scikit-learn. Look at our confusion matrix here, classification report here based on the actuals and predictions. So yeah, the model is doing an okay job. So for example, it seems that it's having a hard time predicting class number 6 compared to the other ones. And let's see what was class number 6. Yeah, these are shirts. Yeah, as you can see, it's actually quite hard to distinguish between maybe t-shirt and a shirt. And let's look at the confusion matrix, and it should help us more where observations the model have hard time to classify what observations. So this is a confusion matrix, and here's a heat map. And as you can see, well, actually there are lots of misclassifications here. So what are they? They are between class 0 and class 6. So between class 0 and 6, between class 1 and 6, 2 and 6, 3 and 6. So it seems that this class 6, whatever it is, we have hard time, the model have hard time predicting that one, especially 0 and 6. I'm curious. Yeah, 0 is t-shirt and 6 is shirt. So again, that makes sense, right? So this is because classifying these things is not the easiest. And remember, this model did 91% accuracy in the test set. So we are seeing quite a few number of errors here. All right, so now I'm going to go ahead and visualize some of these misclassifications and see what were those ones that the model was not able to classify. So we're going to do the same trick that we did last time. So basically, I'm going to create the indices for misclassified images. So by running this one, basically we're making a comprehension list. We say that give me the index for I and X in this enumerate. Remember, if you are enumerating over, well, actually I can show you because I didn't show you last time. So this is what we're doing. So I can say for A and B, well, for A, B in enumerate, let's go ahead and print A and B. You get a better sense of what we're doing, right? So, well, actually, I can go ahead and stop it. And so basically it says that this is the observation number, and these are, if it was correctly predicted or no, right? So now we can scroll down. And yeah, basically these are the indices. So for example, image number 23 was misclassified. Image number 74 was misclassified. I'm going to use these indices to visualize them, right? So here, this is how it's going to look like. Again, the first 9 observations. And let's look at the actually predictions and the actuals, right? So these are predictions, these are the actuals. So what does it mean? It means that the first one, it was, well, let's see if we can, yeah, we can see them all in one. The first one was an ankle boot, right? This is an ankle boot. And the model predicted 5. So what is 5? 5 is a sandal. Okay. The second one in reality was a 4, which is a coat. So this one. So this is a coat. The model classified it as, you know, pullover. And as you can see, this is really hard to distinguish between coat, pullover, shirt, t-shirt. So this in this data set, right? Number 3, I'm curious, what is this one, you know? This is, in reality, is a 3, and 3 is a dress. Okay, and the model predicted 1, which is a trouser. Yeah, you get the idea. This is not a necessarily easy task, even for humans, to classify some of these things, right? But the model is doing an okay job. But remember, we did data augmentation. It didn't help that much for this exercise. But in the next notebook, I'm going to apply data augmentation to real images. And you will see that it's going to perform a lot better there. Okay, until the next one, take care.